Welcome to a comprehensive guide on generating and validating research hypotheses, the foundation of all scientific inquiry. A hypothesis is the beating heart of scientific research, connecting theory to empirical testing. Let's begin by understanding what makes a good research hypothesis. A research hypothesis is a testable prediction about the relationship between two or more variables. In its simplest form, a hypothesis proposes that X leads to or affects Y. The independent variable causes or influences changes in the dependent variable through a causal mechanism. Strong hypotheses share four critical characteristics. First, they must be testable through actual measurements and observations. Second, they must be falsifiable, meaning there must be a way to prove them wrong. Third, they must be specific with clearly defined terms and expected outcomes. Fourth, they should build on existing theory or preliminary evidence, not appear from nowhere. Research hypotheses come in several important forms. The null hypothesis states there is no difference between groups or no relationship between variables. The alternative hypothesis states there is a difference or relationship. Hypotheses can be directional, predicting the direction of effect, non-directional, simply predicting an effect exists, or complex, involving mediating variables. Let's consider a practical example. Does caffeine improve memory performance? The null hypothesis states caffeine has no effect on memory scores. The alternative hypothesis predicts caffeine will improve memory performance. Now let's walk through the systematic process of generating a hypothesis. Step 1 is conducting a thorough literature review to understand existing knowledge. You gather multiple papers, synthesize their findings, and identify gaps where your hypothesis can contribute new knowledge. Step 2 is identifying a specific gap that hasn't been adequately addressed. Ask yourself, what important questions remain unanswered in this field? Step 3 is formulating your preliminary hypothesis based on theory and gaps. Your hypothesis emerges from the convergence of existing theory, available evidence, and the identified research gap. Step 4 is operationalizing your variables, defining exactly how you'll measure them. For instance, memory performance could be operationalized as the number of words recalled in a standardized test. Understanding the statistical foundation is crucial for hypothesis testing. The p-value represents the probability of observing your data, or more extreme data if the null hypothesis is true. The conventional significance threshold is p less than 0.05, meaning less than 5% chance of false positive. This normal distribution shows the critical region where we reject the null hypothesis. The shaded tail represents the 5% significance level. Alpha equals 0.05 is our type 1 error rate, the false positive rate we accept. Beta represents type 2 error probability, failing to detect a real effect. Statistical power equals 1 minus beta. Typically we want power of 0.8 or higher. You might wonder, why is alpha conventionally set at 0.05? It represents a reasonable balance between avoiding false positives and maintaining sensitivity to detect real effects. Statistical significance isn't everything. Effect size matters too. Cohen's d measures effect size as the difference between means divided by standard deviation. Effect sizes are classified as small at 0.2, medium at 0.5, and large at 0.8. Let's apply this to our memory example. Suppose the control group recalls an average of 15 words. The caffeine group recalls 18 words on average, with a standard deviation of 5 words. Cohen's d equals 18 minus 15, divided by 5, giving us 0.6, a medium effect size. Determining adequate sample size is critical for detecting real effects. This formula calculates required sample size based on desired power, significance level, variance, and expected effect. 4 key factors determine your required sample size. First, desired power, typically 0.80 or 80% chance of detecting a real effect. Second, your alpha level, typically 0.05. Third, the expected effect size based on theory or pilot studies. Fourth, the population variance or variability in your measures. Let's calculate sample size for our caffeine study. For a medium effect size of 0.5, alpha of 0.05, and power of 0.80. We need approximately 64 participants per group, or 128 total. This curve shows how statistical power increases with sample size, plateauing around 0.8 at our calculated sample size. Now we design the actual study to test our hypothesis. First, choose a research design appropriate for your hypothesis. Options include experimental designs with random assignment, quasi-experimental without randomization, or purely observational studies. Control for confounding variables that might offer alternative explanations. A confounding variable z affects both x and y, creating spurious correlations if not controlled. Use randomization to distribute confounders evenly and blinding to prevent bias. Systematic data collection ensures validity and reliability. Your measurements must be reliable, producing consistent results. Reliability is the ratio of true score variance to observed score variance. For multi-item scales, Kronbrouwer's alpha above 0.7 indicates acceptable reliability. Validity means your measure actually captures what you intend to measure. High validity means strong overlap between what you want to measure and what you actually measure. After collecting data, we perform appropriate statistical tests. Several statistical tests exist for different hypothesis types. The t-test compares means between two groups using this formula with pooled standard deviation. ANOVA uses the F-statistic to compare multiple group means simultaneously. Chi-square tests categorical data by comparing observed and expected frequencies. Always calculate confidence intervals, not just p-values. A 95% confidence interval provides a range of plausible values for the true parameter. Let's work through a complete example. Control group. 64 participants, mean of 15, standard deviation of 5. Caffeine group. 64 participants, mean of 18, standard deviation of 5. The t-statistic equals 3.39, with a p-value less than 0.001, highly significant. Interpretation requires careful consideration of multiple factors. Does a significant p-value prove your hypothesis is true? No, it only allows you to reject the null hypothesis, not prove the alternative. Statistical significance combined with meaningful effect size leads to practical significance. Always consider alternative explanations for your findings. Let's examine common mistakes in hypothesis testing. P-hacking means testing multiple hypotheses until you find significance, inflating false positives. Multiple testing without correction increases your chance of false discoveries exponentially. The family-wise error rate grows with the number of tests k. Harking means hypothesizing after results are known, pretending you predicted what you found. The solution is pre-registering your hypotheses before data collection. Overfitting occurs when your model is too complex, capturing noise rather than signal. Replication is essential for validating research findings. Research progresses through original studies, direct replications with identical methods, and conceptual replications testing the same idea differently. Successful replication across labs and contexts builds confidence in findings. Meta-analysis statistically combines results from multiple studies. The weighted mean effect size combines individual study effects weighted by precision. Clear reporting is crucial for scientific communication. Always report all relevant statistics, not just significant ones. Include the test statistic, p-value, effect size, and confidence intervals. Example, t of 126 equals 3.39, p less than 0.001, d equals 0.60, 95% confidence interval 1.2 to 4.8. Always discuss limitations of your study transparently. Ethical considerations permeate all aspects of research. Several core principles guide ethical research. Key principles include honesty in reporting all results, transparency in methods and analysis, and respect for research participants. Open science practices like sharing data and code improve transparency and reproducibility. Let's review the complete hypothesis generation and validation process. The complete process involves formulating a hypothesis, designing a study, collecting data, analyzing results, and interpreting findings, always considering ethics and limitations.